Hello, my name is Mike Riley, and in this video I'm going to describe and discuss some of the work that we did for autonomous rendezvous and capture, which is part of the Autonomous Nanotechnology Swarm technology development effort that was headed by Stephen Curtis. The idea that we were working with was a worst-case scenario for a robotic capture of the Hubble Space Telescope. We have been looking into developing robotic technologies for use in irregular or unknown environments because many current robotics technologies are fairly brittle and require very carefully tailored or rather simple environments to deal with. One of the concerns that one has when you are dealing with non-cooperative spacecraft, for example, a spacecraft that is in distress, it may have nonlinear oscillations going on, might be hard to describe, you might collide with the spacecraft. How to build intelligent, onboard, autonomous operating procedures to deal with unknown or uncertain situations is important if you're going to have any confidence in your spacecraft systems and have them behave when you're not capable of monitoring and controlling them. Now, we developed some simulations to look into some ideas of nonlinear control that were based on roughly on some work by Mark Tilden, who came up with an idea of nervous nets. We adapted this to a spacecraft controller in a way very similar to work that had been done previously by Janet Krigo out in Los Alamos. And if we take a look, the files that we're going to look at are in the workspace spacecraft autonomy, and what we did is that we modified some demonstration software that was provided with the Java Astrodynamics toolkit. In particular, their attitude control simulation. We started out with attitude control because that was a fairly simple place. It was a simple place to start, and also showed some of the strongest nonlinear effects that we could look into. So we started looking into adapting the attitude control scenario, and as you can see, there's a whole lot of stuff in here. The box timer trainer is the simulation that I'm going to run today, and it's essentially a reaction wheel attitude control in which the reaction wheels are all hooked up to the nervous nets. We constructed I'm going to open up this terminal over here, and we have a bash shell. We constructed a run script that would actually execute the Java command for the particular simulation that we wanted to run. And you can see there's a number of commands that you can put into it. To actually configure the run for this particular early simulation, you'd actually go in and rewrite the source code for either the box timer trainer itself or other parts of the code. So I'm just going to run the file in this way. Now, I haven't touched this code in 4 or 5 years, and this was one of the last simulations that we did before funding was cut off. We have a simple, cheap model that has a few odd things going on in it. That's why you can see through our little model of the spacecraft. And we grabbed another another little model that would be our chase spacecraft. So here we have the target, here we have the chase spacecraft, and this guy is undergoing some motion here. And as you can see, we're fixed in a particular frame. We're fixed in a frame that's fixed to our chase spacecraft, and this guy is wobbling and weaving, undergoing some sort of complicated motion. In this particular run, we don't really have any sort of control hooked up. We're not sending any sort of commands. There's no estimation of this guy's state, which we then feed through our sensors and intelligent control system over here to try to either chase this guy or match an attitude or anything like that. Okay. But we did have this framework, and actually we're moving towards re-implementing this, or at least taking some of these models and then pushing them over into the TET robotics framework. We're going to have a merging where we use some of the Java Astrodynamics toolkit routines and some of the physics routines that we were using in the TET tetrahedral robotics software, so that we could handle things like collisions and movable members of each of these spacecraft. In this one, we essentially have a very simple rigid body motion that we're dealing with. Okay, although we could get fairly complicated. In fact, the reaction wheels, we have a whole bunch of coupled ODEs in that situation that's actually describing how this guy over here is controlled. All right, so let's go ahead and close this guy off and come over here. Now this movie was made from an old simulation in which the chase spacecraft was ordered to maintain a particular relative orientation with regard to the Hubble Space Telescope, our target spacecraft. And then, right towards the end of this particular simulation, we told the spacecraft to orient yourself with a different relative orientation. And then this guy was supposed to do all the work by itself of reorienting itself. So the only command that we sent over here was, okay, change your orientation to such and such. Now, we had a neural net, an actual neural net, that took that new information and essentially interpreted it so that we weren't really sending this guy, the attitude control system over here, a new number. That number actually had to be interpreted by the onboard neural system, and then that was what controlled the reaction wheels. Okay, so we actually had some simple intelligence being built into the control system. So let's go ahead and see how far we got with this particular set of frames. And here we see the spacecraft, the target spacecraft, moving around, and we see that we're actually maintaining our relative position and attitude. And for this particular run, we didn't catch very much of the actual reorientation. But a new command will come in, and you will see the chase spacecraft change its orientation. There we go. We see that it started to change its orientation. Now, for the particular model that we've chosen, we haven't done any sort of optimization to get rid of any sort of overshoot or anything like that. This was just one of our first attempts to even see if we could get the thing to understand the command. And actually, yes, it did understand the command. It was not tuned, however, to minimize the amount of overshoot, which is something that you would have to do. So this guy, in other simulations, and if I can find one of the movies, I try to provide that to you. But for this simulation, you can see it's starting to realign itself up in the in the right direction, and I hope you believe me on that. But the main point here is that right at this point, we fed it the new positioning information. That positioning information was interpreted by the intelligence software on board, starts to change, and now it's going to go back in and seek the appropriate new orientation. Okay. So once again, this particular run was done 4 or 5 years ago. It was one of our first and one of our last simulation runs of this sort. And what you saw over here with the other simulation was actually a step up beyond what you saw in the previous one. We're starting to get into some translation, starting to get into expanding the amount of intelligence that we had on board the spacecraft. But that first one, we were very pleased to see that the nervous net would actually understand and be able to correctly interpret the new positioning information. So, thank you for your interest in our autonomous capture or autonomous rendezvous and capture simulation that we developed as part of the Autonomous Nanotechnology Swarm and our neural systems software effort. My name is Mike Riley.